Now, what is the alternative? The alternative is bilinear transformation. Now, where does the bilinear transformation came from? Bilinear transformation, no, in this case, what we do is that this was the expression, if you remember, for differentiation. So y of n minus y of n t minus t, right? This is also equivalent to taking integral of its derivative from this value to this value, which means from this value to this value. You do understand that integral is actually area under the curve. This can be approximated by this expression if you go for linear transformation. So we take the average of this value and this value, which is this and this, divided by 2, multiplied by this, multiplied by the difference of these two values, which comes out to be t. So this area under the curve is this value plus this value divided by 2 into the horizontal region. So this integral is actually, you guys have studied the integration and area under the curve, right?
Yes, sir.
So this is linear approximation to it. This expression, and then this is equivalent to, see, this is exactly equal and this is not exactly, this is approximately equal to, because we are not taking the actual curvature, we are taking the linear. This is why it's termed as bilinear transformation. So you won't get exactly the same filter response. There will be slight difference between the two. Now see, now we have this expression and we have this expression, right? Now let's take the Z transform of this one, which comes out to be Y of Z. Let's take the Z transform of this one, which comes out to be Z power minus 1 into Y of Z. Now on this side, we have t by 2. And if we take the Z transform of the derivative of this and derivative of this, which comes out to be these expressions, right? The derivative y dash is actually the dy by dt. And when you go for its transform form, it is going to be s into y. So y1 of z is actually s into y, and it's equivalent z transformation, right? So after rearrangement, we end up with an expression like this, that s is equal to 2 divided by t, 1 minus z power minus 1 divided by 1 plus z power minus 1. This whole process is only explaining that how the transformation is done. You don't have to memorize it, you try to understand it, right? How this is happening, how they are equivalent, right? Otherwise, throughout, you are going to be only using these values. But instead of just pushing you to memorize this, you try to understand where does that came from. So according to this, S has to be equivalent to this when you are replacing it in any of the analog filter to create a digital filter. After rearrangement, you might end up in an expression Z equal to. So if you want to go from a digital filter to analog filter, you can transform it using this, replacing Z by this value. And if you are shifting from an S domain analog filter to digital, then this is your expression. So you have to kind of remember these. They will be available to you as well during the exam. And what is the advantage of this? This provides the whole region rather than just because this after rearrangement, it comes out that this expression has to be less than 1, which means that the whole left plane is actually equivalent to the region inside the unit circle. And this is why bilinear transformation is mostly used. Well, if you don't understand it exactly, what we can do is we will be doing a number of numerical problems, and then you will see the impact of the two. In case you want to compare them, you can use both the methods. You can plot the equivalent response, and you can check it out what's actually happening out there. Okay, that was regarding the Z and S transformation. But you guys actually understand this other thing. You understand the frequency in time domain, and then you understand the normalized frequency in digital domain. So the challenging part is that what is the relationship between those rather than going for S and Z, right? Now we do understand that Z is equal to e raised to power j omega, and S is equal to directly j omega. So this is actually the analog frequency. This is the normalized normalized frequency in digital domain. So z equal to e raised to power j omega, and s is replaced by j omega. This omega is actually 2 pi f, which is the analog angular frequency. You guys remember that, right? And why we are referring to the magnitude of it? Because we first consider the magnitude value and then the phase value. So the magnitude is, they are actually derived from this expression directly. If you look at this expression, z is replaced by e raised to power j omega, s is replaced by j omega, and s is replaced by j omega as well. And we end up with this expression. So if you want to take the phase, so we do understand that for in order to find out the phase of these, we need to take the angle of the first term, angle of this term. Now see, these two are the complex conjugate of each other. So if the first term is going to give you theta, the lower term is going to give you minus theta. And if you do know that the angles are actually added. If you take this angle up, is going to be subtracted, so minus is going to be plus, and you end up with 2 theta, right? You can substitute the values and verify this expression, but you do understand that if you have a plus jb and you have a minus jb, if a plus jb is producing theta, then a minus jb is going to produce minus theta, right? And you do know that the angles are going to be in the form of exponent of theta. So the exponent, if you take the exponent from the bottom to the top, it will be ultimately added with the top one. So theta minus become plus, and it will be 2 theta. Whereas theta, what is theta equivalent to? Now see, we have a real term and we have a conjugate term. So in order to find out is theta, it has to be tangent inverse of the vertical term and divided by the corresponding horizontal term. It's visible from here. See, theta is actually this value divided by this value. Since this value is 2 by t, so naturally the t is going to go up. So we end up with an expression like this, right? Okay, so and if you substitute this theta value into this expression, you will get omega is equal to 2 tangent inverse of omega t divided by 2. Now, what is the basic function of this slide? This slide actually give you a direct transformation method from analog frequency domain to equivalent digital domain. So if you have an analog frequency value, you substitute that value in here. You substitute the sampling frequency value in here, you will get the angular frequency in equivalent digital frequency domain, right? Similarly, if you have a digital filter and you want to see its impact in time domain, right, then you have to shift it into equivalent time domain. And of course, this relationship, after rearranging,